Have you ever noticed how a straw placed in a glass of water appears bent at the surface? This bending of light is called refraction, and today we are not just going to talk about it, we are going to prove it experimentally. In physics, we never take a law at face value, we verify it. This experiment is designed to confirm the two laws of refraction. The first law says that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. The second law, Snell's law, states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction remains constant for a given pair of media. And to put this to the test, we'll be using a rectangular glass block. Why? Because its parallel faces ensure that refraction occurs cleanly and consistently. By the end of this, we'll even determine the refractive index of the glass itself. Before we begin, let's see what we need. Our main player is a rectangular glass block with perfectly polished parallel sides. This is placed on a wide sheet of paper fixed to a drawing board so we can trace every ray. A sharp pencil will help us mark positions precisely, while 4 optical pins will serve as reference points for the path of light. To measure the angles, we'll use a protractor and for lens, a scale. This simple set of tools will let us do something profound, test a fundamental law of nature. First, we place the glass block on the paper and carefully draw its outline. Let's label the rectangle as PQRS. Remove the block for now. On side PQ, choose a point O and draw a perpendicular line, that's a normal, labeled norm. From O, draw an incident ray OU such that it makes a chosen angle of incidence I with a normal, for example, 40 degrees. Place the block back on its outline and fix to pins, labeled A and B, upright along the incident ray OU. These will help us trace how light travels into and through the block. Now comes the exciting part, tracing the emergent ray. Standing on the other side, at face rupees, we look through the block and align 2 more pins, C and D, so that all 4 pins appear perfectly in a straight line. This ensures we are sighting along the actual path of the refracted ray. Once the alignment is perfect, we remove the pins and mark their spots. By joining C and D, we get the emergent ray BC. Next, join O and B, that's the refracted ray orb inside the block. Using our protractor, we measure the angle of incidence I as angle AON and the angle of refraction R as angle BOM. With these, we can calculate sin I and sin R, and finally their ratio, sin I over sin R. Sometimes we want to avoid angular measurements altogether as they can introduce errors. Here's a clever trick. Draw a circle centered at O such that it touches the incident ray OU at D and the refracted ray orb at E. From D and E, drop perpendiculars DF and EG onto the normal norm. Now measure DF and EG. The ratio DF over EG gives us the refractive index directly. Why does this work? In the right triangles formed, sin I equals DF over OD and sin R equals EG over OE. Since OD and OE are equal, the ratio sin I over sin R simplifies to DF over EG, elegant and precise. To be thorough, we repeat the process for several different angles of incidence, say 50 degrees, 60 degrees, 70 degrees, and 80 degrees. Each time, we calculate sin I and sin R and check their ratio. The beauty is, no matter what the angles, the ratio remains constant. This constant value is the refractive index, nu, of the glass block. And by observing that the incident ray, the refracted ray, and the normal all lie in the same plane, we have verified the first law of refraction as well. Our experimental results agree with the theoretical laws within reasonable error limits. So, let's recap. We've experimentally verified both laws of refraction, the geometrical alignment of rays, and the constant sine ratio. We've also learned two practical ways to determine the refractive index through angle measurement and through length ratios. This isn't just a lab exercise, it's the same principle that governs how lenses focus light in cameras, how microscopes magnify the invisible, and how optical fibers carry internet signals across continents. Understanding it bridges the gap between textbook physics and the technology that shapes our world. I hope this session has helped you see refraction not just as a formula, but as a fundamental optical truth. See you next time with another fascinating physics journey.